All right, I'm going to present this one called Long-Lived Transactions Made Less Harmful, from these guys at Hanyang University, and it was at SIGMOD a few years ago. So we have this concept of MVCC and versioning in key value stores and databases too. And the general idea is that if we want some sort of high throughput with reads and writes happening at the same time, we don't want every read to block every write on the same item or the same pair. So what we can introduce is something called MVCC, or multi-version concurrency control. And instead of overwriting a pair or an item or a row in place, what we can do is write new versions of the item, and readers will see an old version when the read begins. So we say, for example, readers can see a view or a snapshot of the database, while other writers can update the same item or row, but the readers see the consistent view. And this depends on how the database is configured or the isolation level. So just as a brief example, we have three items here, A, B, and C, and they each have a timestamp. So TS is timestamp 100, 101, 102. And we have a transaction that starts at timestamp 103. So the transaction wants to read A, B, and C, and that's fine. And now we start a new transaction 2, but its timestamp is 104. So in transaction 2, we write A, we write B, and then we commit. So A and B, after the commit, are now in the database, and that's what readers will see in the future. So notice that transaction 1 isn't finished yet. And in this MVCC model, what will happen is that, let's say transaction 1 wants to read A, but A was just updated by transaction 2 that is already committed. So depending on how the database is configured, what will generally happen is we want to read A here, and because A was updated when the transaction was open, and the read to the latest value of A won't be valid. So we read A, and depending on the database, maybe we'll check the new version first, so 104, and we see that the version or the timestamp of A is greater than the timestamp of our transaction or our snapshot. So this read is not, it will fail or it's not valid. So we can search further, and we search back, and we see that A has another version at timestamp 100, and that's okay because it was created before our transaction started. And then we have another transaction 3 at timestamp 105. It writes A, it writes B, and then it commits. Now, something to keep in mind is that we've created 2 new versions of A and B each, but after transaction 3 commits, we have transaction 1 that's still open, and that's it. So what we can notice is that the versions of A and B in the middle, 104 and 105, can't be seen by anybody anymore, so they can be removed from the store. So it seems pretty straightforward, but there are a few problems. So the first is that when we're creating new versions of stuff in the store the whole time, these old versions are going to take up space. So for example, if we overwrite 100,000 items and we don't have any sort of cleaning mechanism or mechanism for deleting old stuff, we're going to have 100,000 key length, value length, extra space just for those updates. And the issue is that, how do we effectively remove these old items, and how do we find them? First of all, how do we find them, and how do we remove them? And how do we know if it's okay to remove them? Maybe they can be seen by a snapshot or a reader or something like that. Second problem is that readers that are open need to find these old items somehow, through the index or some other way. The problem is that if creating new versions is on the same path as finding old versions in the index, it can cause a lot of problems, a lot of contention. So 2 methods for this, at least in the database world, are in-row and off-row versioning. PostgreSQL uses in-row and MySQL uses off-row, at least when this paper was written. So in this in-row versioning scheme, versions are stored in just a large page called a heap page or heap file. And this heap page or this heap file is indexed by, for example, something like a B tree in memory. So if we want to find a version in the heap page or the heap file, it could be very quick because it's already indexed. But the problem is that if we have a lot of new versions into this heap page or this heap file, the pages are going to get full and we're going to have to split. And while we're splitting, we need to lock the tree, and it hurts concurrency while we split. So as an example, we have a test here where we use PostgreSQL and we run a workload of updates, and somewhere in the middle we start a transaction. And I'm not sure how they did it in the paper, but the transaction doesn't even have to be doing anything. It could just be open at some point in time. So we say we have this long-lived transaction at around this time in the workload. And we notice that as soon as the transaction opens, the throughput starts to drop over time. And at the bottom, we have the CPU usage during all the phases. So when the transaction starts, we use a lot of CPU for scanning versions, and we use a lot of CPU for reorganizing the index. So because of these splits, and then when the transaction finishes, the throughput jumps back up and the CPU usage goes back down. The second method is off-row versioning in MySQL, and instead of placing versions in some sort of heap page that's indexed, we place it in what's called an undo space. So in the diagram, we have lots of versions of A and B just in this long, large undo space. They're not indexed in the same way as the in-row versioning. So the benefit here is that we don't really have page overflows that need to modify the index above, which is good for update throughput. But the issue is that the way we find old versions is through back pointers to the previous version. So in this example, let's say we want to read, let's say our transaction is timestamp 49 or something, and we want to read A in our transaction. We have to go 99, 97, 50, and then 48. So we have 4 reads in this case, just to find one item. That's not so bad, but what if the version chain was thousands of items long? Then it can get really bad. And I think all the while the version search is happening, we have a lock on the item too. I'm not sure about that. So we have the same test, but we do it in MySQL. So we have some update workload or some workload. We open a long transaction, and then we close it. And then we look at the CPU again. And as soon as the transaction starts, we have all this contention on the pages in this undo log. The CPU usage goes up, and the throughput of the foreground transactions drops completely. So in this work, they proposed something called zero versioning, or ZIRO, and it stands for single in-row remaining off-row versioning. And the general idea is that we only keep the first old version of a record on the same page as the latest version. So for the first old version, it's in row, but anything older than the first old version, we keep in off-row space somewhere else. And the general idea here is that when we're opening a lot of short-term transactions, we might only need the first version to be read so we can get it quickly. And so even when a long transaction is open, we can get fast reads for the foreground transactions. But when we move all the old versions somewhere else, we can avoid these like frequent index changes that we might get with normal in-row versioning, because we only have 2 versions on the page. So as a general overview, each data page has the most recent version and the first old version, and they call this, single in-row remaining off-row versioning. So first, the new versions are placed here, and when we update again, the second old version is going to be moved to the off-row space somewhere else. Now, when we read from the page and move it somewhere, I'll explain after, into memory, we check if this item, based on its timestamp, is visible to any reader or any transaction. And at this point, using some heuristic, it's not completely accurate, but at this point, if we decide this item can't be seen by anybody, we can just drop it. We don't need it anymore. We don't need it in the store or anything. So at this point, the pair, the secondal version might just be removed and deleted. In fact, most are. We can tell that most can be deleted here. But if they survive or they're still visible, now we move them to off-row versioning. So first of all, the pairs are moved to a version buffer in memory. And these version buffers are indexed also in memory by this thing called location look-aside buffer. And depending on how long the version is updated or if it's part of a transaction, they're classified in different ways. But we can't just use all the memory, or we can't just use a ton of memory and say, okay. So we have some limit on the size of these version buffers in memory for the old versions. Now, once the buffers are full, they need to be flushed to disk in what they call segments. But before we flush to disk, we try once more to prune the versions. So can we see this in a transaction? Can a reader see it? If not, delete it or just drop it. And anything that survives both prunings is put into a segment on disk. And then later, in the background, we can scan big segments, and if they contain no visible versions for any transaction, we can drop them, we can delete them. So the way the segments work is that we have this index where we point keys and their old versions to either versions that exist in memory right now or versions that exist in storage. So we just have a lot of key pointers with backward links, but because it's in memory, it can be fast. And then we have this list of segments in memory where we have the ID of the segment, but we have the minimum and maximum version in this segment of any pair, not just of one pair. So later, when we're scanning the segments, we can say, is anything in this timestamp visible to a transaction? And if it's not, we can just drop the segment. So when we move pairs to the version buffer or the in-memory buffer here, they can be classified depending on how much they're written or if they're a part of a long-term transaction. So we have three classifications: LLT, cold and hot. If the versions, and the general idea here is that if we place versions of the same type into the same type of segment, the same file, maybe we can clean it more efficiently because things tend to die at the same time. So we have LLT versions if they're visible to a long snapshot, hot versions if they have short update intervals, and then cold versions that have update intervals longer than the hot ones. And just briefly for the segment cleaning, we just check the in-memory stuff for the segment metadata, and we say, does it contain any visible versions? If not, we can just drop it. But the point here is that because we only hold the minimum maximum timestamp of any item in the whole segment, even if there's like one item that's still visible in the entire segment, we can't drop it. So if there's a lot of small items that are still alive, it can hurt the space. So to evaluate, they implemented in MySQL and PostgreSQL and use a pretty powerful machine, and the memory buffer is set at just 8 megabytes, so quite small. And the workload they use is just, I think it's an update workload while there's a long transaction in the background on quite a small database. So what we want to see is, as the long-term transaction begins, what does the throughput look like when we use this scheme? So on the left, so these results are from MySQL, and the red is MySQL and the blue is their scheme vDriver. So on these left graphs, we have uniform, and then on the right, we have skewed. So long-term transaction is this arrow, and we have the throughput, it's okay, before the transaction starts, and for MySQL, as we know, it drops, but it stays stable for vDriver the whole way through. So why is this? The thing is, if we can really quickly and accurately remove old versions from the store, the amount of time we have to hold the lock on a page reduces. And so if we look at the bottom part here, we have the maximum chain length of any version of a pair or an item in the store. So if you, and it's in log scale, by the way. So if you look at MySQL, at least in the uniform case, some of the version chains could be up to, you know, over 100. But with vDriver, I'm not sure what the exact numbers, but I think it's down to like 20 or 30. So with a much shorter chain, when we're searching for an old version, we need to hold the lock for much shorter on the page. So the transactions in the foreground can proceed very quickly while there's a long transaction in the background. And just to look even closer at the length of the version chains, in a skewed workload, because we're updating a small amount of items a lot over and over, the chain lengths for some of the pairs can get very, very long. So in this example, we have chain lengths of versions that are as big as 10 to the power 4. So that's 10 to the power 4 items for one row or just existing on storage somewhere without being cleaned. But when we use this vDriver scheme, we can prune them very quickly, and the maximum length is like 35, so it's not much. Finally, if we look at the segments, so remember, when versions survive pruning, when they move to off-row storage and when they move to disk, they survive pruning, then they're put into a big segment. Well, it depends on the configuration, but they're put into a segment on disk. But the problem is that we can't clean these segments until they're completely full, because the cleaning is based on the minimum version and the maximum version in the segment, and we can't get the maximum or minimum until the segment's closed and flushed to disk. So what happens is that when we have really large segments, so for example, 16 megabyte here, what happens is when the segments get very, very big, they can hold a lot more items. But if the workload is skewed, we could have, for example, so we have like 1,000 items here. They all might be in the same segment, but the segment isn't closed yet. You know, it's because it's really big, 16 megabyte. So in that case, the version chains under the skewed workloads in their scheme could actually get very, very long. And then we can see the same problem as the other stores. I wish they showed the throughput with this one, but they didn't in the paper. They just show the version lengths. So to conclude, long-lived transactions can cause this clash between index maintenance, searching for old versions, while taking incoming updates. And the general idea is that if we can reduce the amount of versions as much as possible, we can make all these problems better or less serious anyway. And they introduced this scheme, SIRO versioning. And now transactions have really fast access to new versions, but because the version chains are so small, even when we're searching for old versions, we spend very little time holding locks and stuff on pages. Thank you.